For some of you, this is your last section of pre-calculus trigonometry. A few of you have a few more sections, but believe me, they're totally simple compared to everything else we've done. But this section is on parametric equations. Suppose that t is a number in an interval I. A plane curve is the set of ordered pairs x, y, where x is f of t and y is g of t for t in interval I. The variable t is called a parameter, and the equations for x and y are called parametric equations. So we're separating out the x and the y to factor in another variable t. And t is usually time. So to graph plane curves, select some values of t. For each value, use it to create parametric equations with x and y and plot the points over the graph. So let's look at an example here. It says graph the plane curve defined by parametric equations x equals t squared plus 1 and y equals 3t. So what we're going to do here is when we plug in for x, we're plugging in t. T is -2. And -2 squared plus 1 is 5. Then we come over here, and for y, we also plug in -2 for t. That gives us -6. So the point that we plot is where x is 5 and where y is -6. So we're going to do that along the line here. So the next one, x is -1 squared plus 1, which is 2. And y is 3 times -1, which is -3. Let's do one more of these together. So if we plug in 0, we've got 0 squared plus 1. That's just 1. And y equals 3 times 0 is 0. And then the last two, that gives us x to be 2 and 5 when you plug those in, same way, and y to be 3 and 6. So what we're going to do is take these points and plot them on our graph. So this has enabled us to have a function in terms of x and y, and also in terms of t, which, like I said, most often is time. So we plot 5, -6. Two, -3. 1, 0. 2, 3. And 5, 6. And so what we've got here is a parabola that opens to the right. So we've graphed it with two functions, but it's not a function. Oh, and because this is only defined, if you'll look back, it said defined between -2 and 2. So that's why we plugged in t -2 to 2. Because it's only defined there, then that means that it actually starts at -2 and moves up to 2 and stops there. So we can actually, this has a direction to it. We can actually put arrows on it because it started here and moved up to there and stopped. eliminating the parameter, it says if we eliminate the parameter in a set of parametric equations, we can write one equation in xy that is equivalent to two parametric equations. So we're just going backwards here, taking our two equations and changing them back into one, eliminating the parameter t and resulting in one rectangular equation in x and y. Keep in mind it may be necessary to change the domain, so you'll see what I mean here. So for example 2, it says sketch the plane curve represented by these parametric equations by eliminating the parameter. Okay, so we've got x equals 4e to the t and y equals negative 3e to the t plus 4. Solve this first equation for e to the t. Okay, I'm trying to get towards getting t by itself. We may not get quite there with this particular problem. But if we solve for e to the t, we're dividing both sides by 4. And so you get x over 4. Now that's a good thing because we've got y equals negative 3 times e to the t plus 4. So we can plug in the e to the t that we solved here, right here. It's x over 4. So you just find something to solve for that involves t, whether it's t or something that's got t with it, and use that to plug into your other equation. So we'll have y equals negative 3/4 x plus 4. Now let's graph this and see what our domain should be. We know we've got y equals, okay, so it's a linear equation. Y-intercept is 4, and the slope is down 3 over 4. So our line looks, see if I can get it a little bit better, something like that. So in this case here, where would our domain be? E is only defined in the positive in this case. So our domain is going to have to be, for our eliminated the parameter function, our domain is going to have to be greater than 0. So I'm just going to erase this part that's negative. And so basically we've got this piece of a line or a ray that's heading down like that. Example 3 says sketch the plane curve represented by the parametric equations by eliminating the parameter. So we're going to do the same thing we did before in idea, and we need to find some way to get rid of the t. Well, we've got cosine and we've got sine. Now, if they were both cosine, it'd be easy. We could solve for cosine, plug into the other one, or vice versa if they were both sine, but they're different. So we have to figure out some way, how are we going to deal with cosine and sine? Well, this might not be the first thing that comes to your mind, but we know that way back in the beginning of the semester and throughout, that if we use the Pythagorean theorem or our Pythagorean identity of trigonometry, then sine squared plus cosine squared equals 1. So that could help us here because we would get rid of the sine and the cosine in that case. So that's very positive. So let's take this and we're going to use the first equation and solve it for cosine. So if we solve this for cosine of t, then we'll divide by 6. There we go. And the second one, we're going to solve for sine. So we would divide y by 4. Now if we go and square both of these, and let's separate that a bit. They're not being multiplied, so here we go. Then that gives us cosine squared would be x squared over 36, and sine squared is y squared over 16. Take this to the next page. Now we can write our Pythagorean identity, where we know that sine squared plus cosine squared equals 1. And so we're just going to plug in what we've solved for sine and cosine. So sine was y squared over 16. And cosine was x squared over 36. So look, we've got some kind of conic here. Goody. Okay. So we've got y squared over 16 plus x squared over 36 equals 1. What kind of conic is this? The bigger number is under the x, and there's a plus in the middle. So because of the plus, it must be an ellipse. Because the bigger number is under the x, the major axis is horizontal. So the bigger number is a, and let's do that. So a squared is 36. Therefore, a is 6. So this is centered about 0, 0, because we don't have any h or k added in here. So we've just got a will be negative 6, 0, because it's along the x, and 6, 0 for the major axis vertices. And then the other two vertices, b squared is 16. So b is 4, so they'll be at 0, negative 4, and 0, 4. So let's go over here and plot these. Got negative 6 and 6, negative 4 and 4. So we've got our ellipse. We can graph that, but let's talk about it for just a second here. Back in the problem, it said we want this ellipse defined between pi and pi over 2. So if we look at our graph and pretend that this is a polar graph for a minute, where would pi to pi over 2 be? Pi starts here and goes around to there. So this is only defined between pi and pi over 2, or in the rectangular axis, only defined in the negative y, below the x-axis. So we can erase this point. And so the parametric equation is only, our ellipse is only this half down here. And since it's starting at pi and going to 2 pi, then that means it must be going in this direction. Okay, few more examples. Finding a parametric equation. So if you've got your function in terms of x and y, how do you take it back to being a parametric equation? So opposite of what we just did. So one set of parametric equations for the plane curve divided by y equals f of x would be x equals t and y equals f of t. So just where x is t and y is f of x, where x is t. So looking at example 4, it says find a set of parametric equations for the parabola. This is not a parabola in the graph. This is a line. Oh, let's change that. For the line in the graph. Okay, so what's the equation for this line? Its y-intercept is at 4. And its slope is up 1 over 1, I think. So the slope is 1. So the equation in y equals mx plus b would be 1x plus 4. Let me move this up so I don't run out of space. Okay, so how do we define this parametrically? Well, it says let x be t and y be f of t. So if y is f of t, we're just plugging in t for y, or for x in f of x. So t plus 4. It was not a 4. So our parametric equations would be x plus t and x equals t and y equals t plus 4. There's our answer. For example 5, it says find a set of parametric equations for the parabola. This time it is a parabola, where y equals x squared minus 25. So again, let x be t. And let y be f of t. So we're just plugging in t for x. T squared minus 25. So our parametric equations are x equals t and y equals t squared minus 25. That might sound really easy to you. It is that easy. I'm glad. Apply parametric equations to modeling. So this is where it really comes in that these are important, because we can do things like find motion where we're taking into account distance and height and time. So 3 different variables with the parametric equations. So it's very useful. It says, let t greater than 0 represent the time under which an object is in motion along a plane curve, and let x naught, y naught represent the initial position of the object at t equals 0. For uniform linear motion, then x will be x naught, the initial, x plus a times t. And y will be y naught plus b times t, where a and b are the horizontal and vertical components of velocity or speed, respectively. And we'll come back to that for the last example. So for example 6, it says an object undergoes uniform linear motion on a straight path from the point 38 to point 610 in 3 seconds. Write parametric equations over an interval I that describes the motion along this path. Okay. So it starts at point A, which is 3, 8. So that means x naught is 3 and y naught is 8. Okay? And t, it tells us, is 3. T is time in seconds. Okay, and before we can write our parametric equations, we need A and B. A is 6 minus 3 over 3. Where did I get that from? This x value minus this x value, okay, over the time. So let's color code that a little bit more. So the second x value, we could just call that x minus x naught over t. So it'd be 6 minus 3 over the t equals 3, not the point, the x value of the point, okay? And then we want to find b. So b would be the second y value minus y naught over t. So 10 minus 8 over t, that's 3. And then we'll simplify these guys. So 3 minus 3, or 6 minus 3 is 3. 3 over 3 is 1. 10 minus 8 is 2. 2 over 3 is 2/3. So we're wanting to write x equals x naught plus at and y equals y naught plus bt. And we found all we need here. X naught was 3. A was 1. And we can simplify that. It's just x will be 3 plus t. And then over here, y equals y naught was 8. And b is 2/3. So our parametric equations are x equals 3 plus t and y equals 8 plus 2/3 t. And that is defining our object over time. Then example 7, let's go back and look at projectile motion. So we're going to be talking about parabolas here, like a rocket or something being shot up in the air. So projectile motion, and we're assuming negligible air resistance, so there's no wind, will be defined as x equals b naught times cosine theta times t plus x naught. Y will be negative 1/2 gt squared, we'll talk about g in a minute, plus v naught sine theta times t plus y naught. What this is x is our distance function and y is our height function. You're going to find this on your lab. So x is distance, which makes sense because it's distance as you run from the left to the right, x-axis. And y is the height as you go up the y-axis. In this case, theta is the angle of launch relative to the horizontal. V naught is the initial speed. G is the acceleration due to gravity. So G is either, depending on whether you're talking about feet or meters, G is either 32 feet per second squared or 9.8 meters per second squared. So you'll use one or other of those in your formulas. So now looking at example 7, it says a ball is thrown from a height of 5 feet at a speed of 80 feet per second and an angle of 60 degrees from the horizontal. Write parametric equations to describe the path of the ball as a function of time t. Determine when the ball hits the ground. Okay, so first off, we need to figure out what's x naught and y naught. Well, x naught is, x naught y is where it's thrown from. It's thrown from a height of 5 feet. So this is our initial starting point. So the distance isn't going to matter. Our distance, x, is just going to be 0. But it's starting up at 5 feet. So that's what makes x naught 0 and y naught 5. We're told that theta is 60 degrees. We're told that the initial speed, v naught, is 80. And we're in feet per second, so that means that g must be 32 feet per second squared. We'll just write 32 for now. Okay? So we're going to use this information to help us out. Move everything up top here. So I got plenty of room. Okay. And change our colors around. So, we'll start with the distance function. And our distance function is defined by x equals v naught cosine theta times t plus x naught. So we're just going to plug in. V naught is 80. We've got cosine of theta, which was 60 degrees. T, we're keeping it in terms of t, plus x naught, which was 0. So now we can simplify that a bit. It'll be 80 cosine 60 degrees t, because no 0 there. And then we will look at our height function. The height function is defined as -1/2 g t squared plus v naught sine theta times t plus y naught. So let's plug in all these things. G is 32. V naught was 80. Theta was 60 degrees. plus y naught, which was 5. Okay, we can simplify this. 1/2, oh, I forgot my negative up here. 1/2 times 32 is negative 1/2 times 32 is negative 16 t squared. Then we have 80 sine of 60 degrees t plus 5. Now we can leave these in terms of cosine and sine, or we could simplify them even further. Either way will suffice. It just depends on what the problem wants you to do. Cosine of 60 is 1/2. So x is just 40t. And then here, sine of 60 is square root of 3 over 2. So y would be simplified as negative 16 t squared plus 40 square root of 3 t plus 5. Hoping I have more space on the next page. Oh, there's not another page. Oh, crummy. Okay. Guess I'm going to have to do some erasing then. Okay. So these are our two functions. So I'm going to erase all this. Of course, it's in your notes. And you can always back up in the video and see it again if you need to. But right now I need to talk about when the ball hits the ground, it said. So here's our two functions. It says determine when the ball hits the ground. So the ball hits the ground. Let's write this out. If you think about it, which function do we use? Do we use the distance or the height? Okay? So when it hits the ground, is that talking about the distance or is that talking about the height? Well, along the distance, it's just, if we're talking about distance, it's just staying along the ground. So that wouldn't make sense. Height is when it goes up and comes back down. So it would make sense that the ball hits the ground when the height function is at 0, or where y equals 0. Okay? So we'll plug in using our height function. That was the second one. And we're just going to plug in 0 for y. And then solve it. I wouldn't want to factor this if I could. Let's use the quadratic formula. So t will be negative b plus or minus the square root of b squared minus 4 times a times c, all over 2 times a. So if we put this in our calculator, the square root of all of that is 5,120, and 2 times negative 16 is negative 32. So we've got the fact that t is equal to negative 40 square root of 3 plus the square root of 5120 divided by negative 32, or t is equal to negative 40 square root of 3 minus the square root of 5120 divided by negative 32. Put each of those in your calculator. And for the first one, we get 4.4. And the second one is negative 0.07. So, which one is your answer? Well, we're dealing with when the ball hits the ground, right? And that is time. So time cannot be negative. So it's not going to be the second answer. It's going to be the first one. 4.4 seconds is your answer. And that concludes our section on parametric equations.